the typical nitrate concentrations, and in our groundwater here, it's all nitrate. Any ammonia that's put on the soil is nitrified. By the time it gets down a couple meters, it's all nitrate. So we can basically do quantitative nitrogen transport just by measuring nitrate. But it's 12, 15, sometimes 20 milligrams per liter, depending on where your well is. If you go down and measure nitrate in the stream, 1.5 or 2. So the question immediately was, where's it going? And being a microbiologist, I immediately said, well, it must be denitrification, because that's the only thing that can actually take it away. So we started doing some core studies and putting in some piezometers in the stream. If I go down 80, 90 centimeters, concentration is still 12, 13 milligrams per liter. Stream is 1.5 or 2. So with the cores, we've actually investigated denitrification, and we can remove all the nitrate that comes through. There's an issue with residence time, because the first question that I asked after we're seeing nitrate, yet denitrification can take it all out, is where is it coming from? How come there's any nitrate in there at all? Turns out that as you can imagine, the stream bed is incredibly heterogeneous. Some areas pass water very quickly, some areas pass water very slowly. The amount of nitrogen removal is directly related to the residence time of the water that's discharging. So water moves through quickly, it retains some nitrate. Water moves through slowly, all of the nitrate's taken out of it. So we get a mix of fast and slow water coming through the sediments here, and I think that accounts pretty much for the nitrogen that's here. Stage change of about 30 centimeters is adequate to change from a net negative nitrate flux to a net positive, an increase in the nitrate. There's organic nitrogen in there, 30–40% of the nitrate values, but there's never any ammonia. In 8 years of making measurements in this stream, I've never seen ammonia once. The other thing we looked at is diurnal patterns. Art mentioned evapotranspiration. It turns out that we can watch the stage in the stream change over the course of 24 hours on order of 5–6 centimeters. That change is enough to change the residence time slightly, and we can also see diurnal signals in nitrate in the stream. And we've got the observations. Now we're trying to figure out exactly what the mechanisms, if there's anything other than just a change in residence time. And then finally, the thing that we've done is we've done a series of seepage meter studies in here, looking at spatial heterogeneity of the actual discharge. And any place that you have a large amount of discharge per time, the discharge rate is high enough, nitrate concentration goes up. So it goes back to that residence time argument, again, in terms of controls on nitrate in the stream. This thing is an unfinished project that we started a couple years ago. We've been working on transients, storms, changes in stage. Your graduate students get really upset with you when you make them camp out here for a month waiting for it to rain. So the idea is when we get the flume finished, we'll have a segment of the hill slope isolated. We can change the stage at will and simulate storms. And then by penetrating this block in the middle, we'll be able to go in and look at changes in gradients, changes in concentration, and so forth.